we're talking about is the similarity ratio. That would be the ratio of the lengths of the corresponding sides of similar polygons or solids. This is also known as a scale factor. So we've discussed the similarity ratio or scale factor numerous times now. And the way you get the similarity ratio or scale factor is by creating a ratio of a pair of corresponding sides between your similar polygons or solids. So if we know that quadrilateral ABCD is similar to quadrilateral EFGH, the way I would create a similarity ratio or scale factor is by creating a ratio of a pair of corresponding sides. So segment AB we know corresponds with segment EF. So if I take the measure of segment AB and put it over the measure of segment EF and simplify that down, that would be a similarity ratio or scale factor between these two quadrilaterals. And now the cool thing is that because these two quadrilaterals are similar, that ratio should be the same for all four pairs of corresponding sides between these two similar polygons. Meaning, if I put the measure of segment BC over the measure of segment FG and simplify that down, it'll equal the exact same thing we got when we put the measure of segment AB over the measure of segment EF and simplified that down. Same thing for the other two pairs of corresponding side lengths. Next, let's talk about similar solids. Those would be solids that have the same shape with corresponding dimensions that are proportional. So down here, you can see an example of two similar solids. We have two rectangular prisms, and we know that these are similar solids because their corresponding dimensions are proportional. Meaning, if I were to create a ratio between any of the pairs of corresponding dimensions here, they would all simplify down to the exact same ratio, and that would be your similarity ratio or your scale factor. So watch, if I take this pair of corresponding side lengths and put them in a ratio with one another. So 8 inches over 4 inches and simplify that down. I get 2/1. Now if I create a ratio with another pair of corresponding side lengths, this 4 inches over this 2 inches and simplify that down, I get 2/1. If I create a ratio with the heights of these prisms, 6 inches over 3 inches and simplify that down, I get 2/1. All three pairs of dimensions between these two solids have the exact same ratio, meaning this would be your similarity ratio or scale factor, and meaning that these two solids would be similar. Now let's quickly review perimeters and areas of similar figures. This is going to help us out today. So if you recall, if we have two similar polygons, here we have parallelogram ABCD, and we know that that is similar to parallelogram EFGH. If you want to create the similarity ratio or scale factor, all you have to do is just take one pair of corresponding side lengths, put them in a ratio, and simplify that down. So if I create a ratio with the measure of segment AD and put that over the measure of segment EH, because those two correspond with one another, and simplify that ratio down, I get 3/2. That would be our similarity ratio or scale factor. Now the cool thing is that that similarity ratio or scale factor is the exact same as the ratio of the perimeters of these polygons. Meaning, if I were to find the perimeter of parallelogram ABCD and put it over the perimeter of parallelogram EFGH and simplify that ratio down, it should still be the exact same ratio as our similarity ratio or scale factor. And last but not least, the ratio of the areas of these two similar polygons is actually going to be the square of the similarity ratio or scale factor. Meaning, if I find the area of each of these similar polygons and put them in a ratio and simplify that ratio down, it's actually going to be equal to the square of our similarity ratio, which we see that it is here. Now let's talk about the areas and volumes of similar solids. So this says if the similarity ratio or scale factor of two similar solids is A over B, then A over B is going to be the ratio of the perimeters of their bases, A squared over B squared is going to be the ratio of their areas, and A cubed over B cubed is going to be the ratio of their volumes. So down here we have a pair of similar solids. These would be similar rectangular prisms. Now, just like with similar polygons, if we want to find the similarity ratio or scale factor, we just pick one pair of corresponding dimensions and put them in a ratio and simplify that ratio down. So if I take this 8 inches over this 4 inches, simplify that down, that'll equal 2/1. That would be my similarity ratio or scale factor between these two similar solids. And again, you could have picked any of the corresponding dimensions and you should get that exact same similarity ratio or scale factor. Now, whatever that similarity ratio or scale factor is, that is going to hold up for the ratio of the perimeters of their bases. So if I find the perimeter of this base over here, of this rectangular prism, and put it over the perimeter of the corresponding base in the other similar rectangular prism and simplify that ratio down, it should end up being the exact same ratio as my similarity ratio or scale factor. Next, if I were to find the lateral areas or surface areas of these two similar solids and put those in a ratio and simplify that ratio down, that ratio will end up equaling the square of our similarity ratio or scale factor. So to show you that this is true, in this example, I found the surface area of each of these similar solids and put them in a ratio and simplified that ratio down, and I end up getting 4/1, which is the exact same thing as the square of our similarity ratio. So that's how that works. Last but not least, if I were to find the volume of each of these rectangular prisms and put that in a ratio and simplify that ratio down, that ratio should end up equaling the cube of our similarity ratio or scale factor. And to show you that that's true, I found the volume of each of these rectangular prisms and put that in a ratio and simplified those down, and I end up getting 8/1, which is the exact same thing as the cube of our similarity ratio or scale factor. Now we're going to be using all of these today, so make sure you know that the similarity ratio or scale factor, if that's A over B, then A over B is also the ratio of their perimeters. A squared over B squared is going to be the ratio of their areas, lateral and surface, and then A cubed over B cubed is going to be the ratio of their volumes.
All I want for Christmas is example time.
Now example 1 says determine whether each pair of solids is similar, congruent, or neither. If the solids are similar, state the scale factor, large to small. So here we are given two triangular prisms, and we're tasked with determining whether they are similar, congruent, or neither. So the way this works is we're going to create a proportion, and this is going to be an extended proportion where we have ratios of all three pairs of corresponding side lengths. And we're going to see if they all simplify down to the exact same ratio. If they do, then that would be the similarity ratio or scale factor. If they don't, then these two prisms would not be similar. So let's create that extended proportion where we have the ratios of all three pairs of corresponding side lengths set equal to one another. Now what we're going to do is we're going to simplify down each of these ratios and see if they come out equal. And we see that 9/3 simplifies down to 3/1. 3/1, that's already simplified, so we just leave that 3/1. And 6/2 simplifies down to 3/1, meaning all three pairs of corresponding side lengths simplify down to the exact same ratio, meaning that that would be your similarity ratio or scale factor, and these two triangular prisms would be similar.
I gotta go see Rudolph. You try.
Okay, doing the same thing, except this time we're given two cylinders. So in order to figure out if these two cylinders are similar, congruent, or neither, we need to create a proportion. In that proportion, we're going to set up a ratio of each of the corresponding dimensions. So we're going to put the height of one cylinder over the corresponding height of the other cylinder, and we're going to put the radius of one cylinder over the corresponding radius of the other cylinder. And we're going to simplify those ratios down and see if they come out to be the exact same ratio. If they do, then these two cylinders would be similar. If they don't, then they are not. So 14/10 simplifies down to 7/5. 6/4 simplifies down to 3/2. These two ratios are not the same, meaning that these two cylinders cannot be similar. Now example 2 says given the following similar solids, state the scale factor, the ratio of their areas, and the ratio of their volumes, large to small. So in our example down here, we're given two hexagonal pyramids, and we're told that they are similar solids, and we're tasked with finding the scale factor, ratio of their areas, and the ratio of their volumes. So let's start with finding the scale factor because we are given one of the pair of corresponding dimensions. We're given the height of each of these pyramids. So in order to find the scale factor or similarity ratio, what you do is just set up a ratio of those corresponding heights. Now, because we're going from large to small, we're going to take the height of our large pyramid and put it over the corresponding height of our smaller pyramid. Now, what does 6/4 simplify down to? That would be 3/2. That would be the similarity ratio or scale factor between these two similar solids. Next, if I know the similarity ratio or scale factor, I know the ratio of the perimeters of their bases because it's the exact same ratio. It's also 3/2, meaning if I were to find the perimeter of the base of our large hexagonal pyramid and put it over the corresponding base in our smaller hexagonal pyramid and simplify that ratio down, it would equal 3/2. Next, we're going to find the ratio of their areas. Now, in order to find the ratio of their areas, all you have to do is just take the similarity ratio or scale factor and square it. So if I square 3/2, I square the numerator and denominator, and I end up getting 9/4. Meaning, if I were to find the lateral or surface area of either of these hexagonal pyramids, put those corresponding areas in a ratio and simplify that ratio down, it would equal 9/4. Last but not least, if I want to find the ratio of their volumes, what I'm going to do is I'm going to take the similarity ratio and I'm going to cube it. So I cube the numerator, cube the denominator, and I end up getting 27/8. Meaning, if I were to find the volumes of each of these hexagonal pyramids, put them in a ratio and simplify that down, that ratio would equal 27/8. Part B, doing the same thing. We this time have triangular pyramids, and we're given one of the corresponding side lengths in each of these triangular pyramids. Since we know that they are similar solids, we can find the scale factor or similarity ratio by just creating a ratio of one pair of corresponding side lengths. So I'm going to take this 72 feet and put that over the 12 feet because we're going from large to small. And if I simplify that ratio down, I end up getting 6/1. Now that would be the similarity ratio or scale factor between these two triangular prisms. Now if I know the similarity ratio or scale factor, factor, I also know the ratio of the perimeters of their bases because those ratios are equal to one another. Meaning, if I were to find the perimeter of one of the triangular bases in this large triangular prism and put it over the perimeter of one of the triangular bases in this small triangular prism and simplify that ratio down, it would equal 6/1. Next, we want to find the ratio of the areas between these two similar solids. So, the ratio of the areas, remember, is equal to the square of the similarity ratio or scale factor. So, if I square 6/1, I square the numerator and denominator, and I simplify that, I end up getting 36/1. Meaning, if I were to find the lateral areas or surface areas of each of these triangular prisms and put those in a ratio and simplify those down, that would equal 36/1. Last but not least, I want to find the ratio of the volumes of these triangular prisms. So, in order to find the ratio of the volumes, all I have to do is take the similarity ratio or scale factor and cube it. So, I'm going to cube the numerator and denominator. 6 cubed is going to be 216. 1 cubed is still 1. Meaning, if I were to find the volume of this large triangular prism and put it over the volume of this smaller triangular prism and simplify that ratio down, it would equal 216/1.
Make sure you leave out some milk and cookies for Santa, and then you try.
Okay, doing the same thing. We still need to find all of those ratios, and we're going from small to large this time, so note that. Also this time, we are given the surface areas of each of our similar solids. We're not given a pair of corresponding side lengths. So all that means is we need to start by finding the ratio of their areas. So we're going to take the surface area of our smaller solid and put it over the surface area of our larger solid and simplify that ratio down, and that will equal the ratio of our areas. Now, if we know the ratio of our areas, we can find the similarity ratio or scale factor because, remember, if the similarity ratio or scale factor is A over B, then the ratio of the areas is A squared over B squared. So to go the other way, if I know the ratio of the areas, I'm going to have to actually square root the numerator and denominator in order to get the similarity ratio or scale factor. What is the square root of 9? That's going to be 3. What's the square root of 16? That's going to be 4. So 3/4 is going to be the similarity ratio or scale factor between these two similar solids. Meaning, if I were to create a ratio of a pair of corresponding side lengths in these two similar solids and simplify that down, it would equal 3/4. Next, if we know the similarity ratio or scale factor, we also know the ratio of the perimeters of their bases because those ratios are equal to one another. Meaning, if I were to find the perimeter of the base of the smaller rectangular prism and put it over the perimeter of the corresponding base in the larger rectangular prism and simplify that ratio down, it would equal 3/4. Next, if I know the similarity ratio or scale factor, I also can figure out the ratio of the volumes. So in order to find the ratio of the volumes, remember, you take the similarity ratio or scale factor and cube it. So if I cube the numerator and denominator, I end up getting 27/64. Meaning, if I were to find the volume of the smaller rectangular prism and put it over the volume of the larger rectangular prism and simplify that ratio down, that ratio would equal 27/64. Part B, we again want to find all of these ratios, and we're this time given two similar cones and the surface areas of each of those cones. So, because we're given these surface areas, let's start by finding the ratio of their areas. All we have to do, because we're going from small to large, is take the surface area of the smaller cone, put it over the surface area of the larger cone, and simplify that ratio down. That will be the ratio of their areas. Next, because I know the ratio of their areas, I can find the similarity ratio or scale factor between them. Remember, if the similarity ratio or scale factor is A over B, then the ratio of their areas is going to be A squared over B squared. So to go the other way, I'm going to have to square root the ratio of their areas to get the similarity ratio or scale factor. So the square root of 16 is going to give me 4. The square root of 25 is going to give me 5. So 4/5 is going to be the similarity ratio or scale factor between these two similar cones. Meaning, if I were to take the radius or height of this smaller cone and put it over the corresponding radius or height of this larger cone and simplify that down, that ratio would equal 4/5. Next, because I know the similarity ratio or scale factor, I also know the ratio of the perimeters of their bases or the circumference of their bases. It's going to equal the exact same ratio. It's going to be 4/5. So if I were to find the circumference of the base of the smaller cone and put it over the circumference of the base of the larger cone and simplify that ratio down, it would equal 4/5. Last but not least, I can find the ratio of their volumes by cubing the similarity ratio or scale factor. If I take 4/5 and cube that, it should give me the ratio of their volumes. So 4 cubed is going to be 64, 5 cubed is going to be 125. Meaning, if I were to find the volume of the smaller cone and put it over the volume of the larger cone and simplify that ratio down, it should equal 64/125. Example 3, doing the same thing. We still need to find all of those ratios. We're going from large to small this time. We're given two hexagonal pyramids, and we're given the volumes of those two hexagonal pyramids. Interesting. So if you're given the volumes of these two similar solids, we obviously need to start by finding the ratio of the volumes. So to find the ratio of the volumes, going from large to small, we just take the volume of the larger hexagonal pyramid, put it over the volume of the smaller hexagonal pyramid, and simplify that ratio down. Now the interesting thing here is that this ratio doesn't simplify down any. This is as simplified as that gets. So I know the ratio of the volumes. volumes. Now, with the ratio of the volumes, I can find the similarity ratio or scale factor. And you think, how does that work? Well, if I know the similarity ratio or scale factor is A over B, then the ratio of the volumes is going to be A cubed over B cubed. So to go the other way, to go from the ratio of the volumes to the similarity ratio or scale factor, I'm going to have to cube root the ratio of the volumes, meaning I'm going to cube root the numerator and cube root the denominator here. And when I do that in my calculator, the cube root of 343 is going to be 7. The cube root of 216 is going to be 6. And if you don't know what a cube root does, it asks what number cubed gives you 343. That would be 7. What number cubed gives you 216? That would be 6. So now I found the similarity ratio or scale factor between these two similar solids. Meaning, if I were to set up a ratio between two corresponding side lengths or the corresponding heights here and simplify that ratio down, it would equal 7 over 6. Next, since I found the similarity ratio or scale factor, I've technically also found the ratio of the perimeters of their bases here because they're the exact same ratio. Meaning, if I were to find the perimeter of this hexagonal base in our large hexagonal pyramid and put it over the perimeter of this hexagonal base in our smaller hexagonal pyramid and simplify that ratio down, it would equal 7 over 6. Last but not least, I can find the ratio of the areas by taking the similarity ratio or scale factor and squaring it. So if I square the similarity ratio or scale factor, if I square the numerator and denominator, I end up getting 49 over 36. Meaning, if I were to find the lateral or surface areas of these two similar solids, put them in a ratio and simplify that ratio down, it would equal 49 over 36.
I can't try anymore, you try.
Okay, doing the same thing. And again, we are given two similar solids and the volumes of those solids. Meaning, the first ratio we should find is the ratio of the volumes. So to find the ratio of the volumes going from large to small, we're going to take the volume of our larger cone and put it over the volume of our smaller cone. And we're going to simplify that ratio down. The pi's cancel out, and 1,458 over 16 simplifies down to 729 over 8. This would be the ratio of the volumes. Now, if I know the ratio of the volumes, I can find the similarity ratio or scale factor. Because remember, the similarity ratio or scale factor, if that's A over B, then the ratio of the volumes is A cubed over B cubed. Meaning, to go the other way, to go from the ratio of the volumes to the similarity ratio or scale factor, I need to cube root my ratio of my volumes. So I'm going to cube root the numerator and denominator, and in your calculator, when you cube root 729, you end up getting 9. In your calculator, when you cube root 8, you get 2. So the similarity ratio or scale factor between these two similar cones is 9 over 2. Meaning, if I were to create a ratio of the corresponding radii or height in each of these cones and simplify that ratio down, it would equal 9 over 2. Now, because I found the similarity ratio or scale factor, I have also found the ratio of the perimeters of their bases, or in this case, circumference of their bases, because these two ratios are the exact same. So if I were to find the circumference of the base of this larger cone and put it over the circumference of the base of this smaller cone and simplify that ratio down, it would equal 9 over 2. Last but not least, I can find the ratio of the areas by taking the similarity ratio or scale factor and squaring it. So if I square the numerator and denominator, I end up getting 81 over 4, which means that if I were to find the lateral or surface area of each of these cones, put them in a ratio and simplify that ratio down, it would equal 81 over 4. Now, example 4 says two rectangular prisms are similar. The surface area of the first prism is 52 feet squared, or square feet, and the surface area of the second prism is 208 feet squared, or square feet. If the volume of the second prism is 192 feet cubed, or cubic feet, what is the volume of the first prism? So in a problem like this, it's important to sketch it out. We have two rectangular prisms that are similar. We know the surface area of the first prism is 52 feet squared. We know the surface area of the second prism is 208 feet squared. And we know the volume of the second prism is going to be 192 feet cubed. And we're tasked with finding the volume of the first prism. So we're going to say the volume of this first prism is x. So that's what we're trying to find. So now, based on what we're given, how do we find this? Well, since we're given the surface areas of both of these rectangular prisms, what we could do is we could find the ratio of the areas between these two similar prisms. Then, using that ratio, we could find the similarity ratio or scale factor. And with the similarity ratio or scale factor, we could then find the ratio of the volumes. And with the ratio of the volumes, we could set up a proportion and solve for our missing volume. So that's how this is going to work. So first, we need to find the ratio of the areas. So we set up a ratio of these two surface areas here. We're going to take 52 feet squared, put it over 208 feet squared. We simplify that ratio down, we end up getting 1 over 4. So that's going to be the ratio of the areas of these two similar prisms. Now, we can use that ratio in order to find the similarity ratio or scale factor. Remember, if the similarity ratio or scale factor is A over B, then the ratio of the areas is going to be A squared over B squared. So to go the other way, I'm going to have to square root the ratio of the areas to get the similarity ratio or scale factor. So 1 squared is going going to be 1, 4 squared is going to be 2. So the similarity ratio or scale factor between these two similar solids is 1 over 2. But again, we're not trying to find a missing side length or a missing dimension. We're trying to find a missing volume, so we need the ratio of the volumes. Now remember, the ratio of the volumes is just the cube of our similarity ratio. So we're going to take our similarity ratio or scale factor, we're going to cube it, and that's going to give us the ratio of the volumes. Now again, what this means is if I were to find the volume of this smaller rectangular prism and put it over the volume of this larger rectangular prism and simplify that ratio down, it would equal 1 over 8. So what we can do then is use this in order to set up a proportion to solve for our missing volume. On one side of our proportion, one of our ratios is going to be the ratio of the volumes, 1 over 8. On the other side of our proportion, we're going to have the ratio of the two actual volumes, x over 192. Now all we have to do is just cross multiply and solve for x, our missing volume. And when we do that, we get 8x is equal to 192, divide both sides by 8. We get x, or the volume of our smaller rectangular prism, is 24 feet cubed, or cubic feet.
I make the best presents, but you can try.
Okay, doing the same thing, except this time we have two triangular prisms, and we know that they are similar solids. We also know that one side of the larger triangular prism is 1.8 meters, and the corresponding side of the smaller triangular prism is 0.4 meters. The surface area of the larger triangular prism is 12 square meters, and we're trying to find the surface area of the smaller triangular prism, so we're going to call that x. So in order to find our missing surface area here, what we're going to do is, because these two solids are similar, we can set up a ratio of the corresponding side lengths here and simplify that ratio. That will then give us the similarity ratio or scale factor. Then what we can do is we can square that to find the ratio of the areas. Then we can set up a proportion with the ratio of the areas and our two actual surface areas to find our missing surface area. So that's how this works. We're going to start by finding the similarity ratio or scale factor between these two similar solids. Now how do we find the similarity ratio or scale factor? Well, again, you just create a ratio of a pair of corresponding side lengths. So here that would be this 1.8 meters. We're going to put that over this 0.4 meters. Now we need to simplify this ratio. How do you simplify a ratio with decimals in it? Well, you need to get rid of the decimals. So we're going to multiply this by a form of 1, and it's going to be 10 over 10. The reason is because if I multiply this by a form of 1, it doesn't actually change the ratio. And if I multiply by 10 in the numerator and 10 in the denominator, there will no longer be any decimals in this fraction. Now I can simplify this, and I end up getting that the similarity ratio or scale factor between these two similar triangular prisms is going to be 9 over 2. Now I can use that similarity ratio or scale factor to find the ratio of the areas, because all I have to do to find the ratio of the areas is just square the similarity ratio. So what is 9 squared over 2 squared? That's going to be 81 over 4. That's going to be the ratio of the areas. Meaning, if I were to take the surface area of the larger triangular prism and put it over the surface area of the smaller triangular prism and simplify that ratio down, that would equal 81 over 4. So we're going to use this in order to help us find the surface area of our smaller triangular prism. The way we do that is we set up a proportion. On one side of our proportion, the ratio is going to be the ratio of our areas, 81 over 4. On the other side of our proportion, it's going to be a ratio of the actual surface areas, 12 over x, what we're missing. Now all you have to do is just solve this given proportion by cross multiplying. When we cross multiply, we end up getting 81x is equal to 48. We then divide both sides by 81. We get x is approximately equal to 0.59 meters squared, or square meters, meaning the surface area of our smaller triangular prism over here is going to be 0.59 meters squared, or square meters. Now, word problem says a company sells two different types of basketballs. The ratio of their circumferences is 5 to 3. If the circumference of the smaller ball is 8 pi inches, find the volume of the larger ball. Round your answer to the nearest thousand. So step 1 in a word problem, we're not scared, we can do this. Step 2, what is this question asking us to find? It's asking us to find the volume of the larger ball. So we have two different types of basketballs, one larger, one smaller. And we are trying to find the volume of the larger ball. We'll call that x. Now, what are we given? We're given that the ratio of their circumferences is 5 to 3. Okay, that'll come in handy later on. What else are we given? We're given that the circumference of the smaller ball is going to be 8 pi inches. So we can say that the circumference of this smaller basketball is going to be 8 pi inches. Now, in order to find the volume of this larger ball, there's actually a couple different ways you could solve this problem. One would be to use this circumference of the smaller ball to find the radius of the smaller ball, and then set up a proportion with this similarity ratio, or this scale factor right here, in order to find the ratio of the larger ball. And then that could help you find the volume of the larger ball. I'm going to do it a little bit differently though. I'm going to take the similarity ratio or scale factor, 5 to 3, and I'm going to use that to create the ratio of the volumes. Then I'm going to find the volume of the smaller ball and set up a proportion with the volume of the smaller ball and the ratio of the volumes to find the volume of our larger ball. So let me show you how that works. Again, first thing I want to do is find the similarity ratio or scale factor. And the cool thing is that they give us that. The ratio of the circumferences is the ratio of the perimeters, which is the exact same thing as the similarity ratio or scale factor. So we know our similarity ratio or scale factor is 5 to 3, or 5 over 3. Next, we can use that in order to find the ratio of the volumes. In order to find the ratio of the volumes, you just take the similarity ratio or scale factor and you cube it. So we're going to cube our 5 and our 3, and we end up getting that the ratio of the volumes of these two basketballs is 125 to 27. Meaning, if I were to find the volume of the larger basketball and put it over the volume of the smaller basketball and simplify that ratio down, it would equal 125 to 27. So this is going to help us in finding the volume of the larger basketball. What we need to do first is find the volume of this smaller basketball, and we can use its circumference in order to help us. So to find the volume of the smaller basketball, what I do is I take the circumference of the smaller basketball and I set it equal to the circumference formula, 2 pi r. The reason is because now I can solve for the radius of my smaller basketball by just dividing both sides by 2 pi. I get the radius of the smaller basketball is 4 inches. Now, why does that help us? Because if I know the radius of the smaller basketball, I can find the volume of the smaller basketball, because the volume of a sphere formula is 4/3 pi r cubed. So I take 4 inches, plug that in for r here. I then cube that, multiply it to 4/3 and pi, and I end up getting that the exact volume of this smaller basketball is 256 over 3 pi inches cubed. And as you can see, we're leaving it in exact form, because if we round too early, we'll get the wrong answer. Now that I know the volume of the smaller basketball, I can set up a proportion in order to solve for the volume of the larger basketball. In a proportion, I have two ratios set equal to one another. On one side of my proportion, I'm going to have the ratio of the volumes, 125 over 27. On the other side of my proportion, I'm going to have the actual volumes, x over 256 over 3 pi inches cubed. Now all I have to do to find the volume of the larger basketball is just cross multiply and solve for x. So when I do that and divide both sides by 27, I get x is approximately equal to 1,241.123 inches cubed, or cubic inches. Now, because it's a word problem, you need to answer in a sentence. We found that the volume of the larger basketball over here is equal to 1,241.123 inches cubed, or cubic inches.